Let's understand fluid mechanics in this video.
Have you ever wondered why a diver feels more pressure the deeper they go? Or why a barometer tells the weather?
Today we will connect those everyday ideas to simple physics rules you can use for problems. First, what is a fluid?
A fluid is any substance that keeps flowing when you apply a small sideways push. So it includes liquids and gases.
Now, density tells us how much mass is packed in a unit volume. If we call density rho, it means mass divided by volume, and its SI unit is kilogram per meter cube. Relative density or specific gravity is a comparison number. It is the ratio of a liquid's density to the density of pure water at 4 degrees Celsius. Specific gravity is nearly the same as relative density, and it has no units. Next, pressure in a fluid is the normal force per unit area that the fluid exerts on a surface. Pressure acts perpendicular to any surface in the fluid. So pressure does not have a direction and is a scalar. The SI unit of pressure is the Pascal, which means Newton per meter squared. Atmospheric pressure is the pressure of the air around us, and a typical value at sea level is about 1.013 times 10 to the 5 Pascal. Now let us see how pressure changes with depth in a fluid. Consider a thin horizontal slice of fluid with area A and thickness dy at some depth. The upward force on the slice is pressure at the bottom times area, that is P times A. The downward force from above is pressure at the top times area, which is P plus delta P times A. And the slice has weight rho g A dy. In equilibrium, the upward force minus the downward force minus the weight equals 0. From this we get delta P equals minus rho g delta y, which means pressure decreases as we move up. Integrating gives P at depth equals P naught plus rho g h, where P naught is pressure at the free surface and h is the depth below that surface. So pressure increases linearly with depth when density and gravity are constant. One useful device is the barometer, which measures atmospheric pressure using a tall column of mercury. If the mercury column height is 760 mm, we use P naught equals rho g h to compute atmospheric pressure. Using rho equals 13.6 times 10 to the 3 kilogram per meter cubed, g equals 9.8 meter per second squared, and h equals 0.76 meter, we get about 1.01 times 10 to the 5 Newton per meter squared. A manometer is a U-tube used to measure gas pressure, and the gas pressure minus atmospheric pressure equals rho g h, which is the gauge pressure. Let us try a short-solved example on the manometer idea. Question number 1. A U-tube shows a height difference between mercury levels. Find the gas gauge pressure. The solution uses gauge pressure equals rho g h. So measure h, multiply by the mercury density and by g, and you get the pressure difference between the gas and atmosphere. Next, consider the force on a vertical side wall filled with liquid of height h and width b. Take a thin horizontal strip at depth x with thickness dx. Its force df equals pressure at x times area, which is rho gx times b dx. Integrate df from x equals 0 to x equals h to get total force F equals rho gb times h squared divided by 2. That shows the average pressure on the wall is half the pressure at the bottom. The same strip idea gives the torque on the wall about the bottom edge by adding a moment arm. Integrate to get torque proportional to rho gb times h cubed divided by 6. Now let us look at fluids in accelerating frames and rotating containers. When a container accelerates, the free surface tilts so that the effective gravity points normal to the surface. Pressure at any point still follows P equals P naught plus rho g times the effective depth measured along the effective gravity direction. In a rotating bucket, there is a radial outward pseudo-force, and the free surface becomes a parabola. For pressure at a radius r from the axis,
The result is P equals P naught plus rho times omega squared times r squared divided by 2, where omega is the angular speed. Let us solve that rotating bucket result step by step. Take a small radial slice and write the equilibrium relation dp equals rho times omega squared times r dr, because the pseudo acceleration is omega squared times r. Integrate from the axis where pressure is P naught to radius r to get P minus P naught equals rho times omega squared times r squared divided by 2. So the pressure rises with the square of the radius in a rotating liquid. So what do we learn from this? We learn that density links mass and volume, pressure is force per unit area and increases with depth as rho gh. And similar formulas work in accelerating or rotating frames with effective forces. Let us quickly remember the main points. Density, relative density, pressure definition, hydrostatic formula P equals P naught plus rho gh, manometer and barometer use rho gh, and rotating fluids give a pressure that grows like omega squared r squared divided by 2. Keep practicing these steps on slices and integrals. They make many fluid problems simple. Thanks for watching. Keep exploring more questions and notes on EduRev. And remember, learning is a steady, friendly process.